Hello. 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 All right. All right, we were looking at the switch statement and how the compiler uses a clever trick to translate the switch statement. There is a lesson that we need to learn here, and the data structure that the compiler uses is the jump table. So the key idea is, if we were to translate the switch statement using a number of if-else statements, we would end up with a lot of branch statements, and we would have to do a lot of comparisons to figure out what sequence of instructions do we really need to execute. And you know how branches translate into assembly. So the code, if you have more case statements here, this is a switch. We say that X is a switch, and then X could have different values, whoever calls this function. And the intention of the programmer is to execute the code corresponding to one of the cases here. So when we are done executing code for case 3, a break statement will take us out of the switch statement and to return. Okay, so a jump table stores the target addresses of a jump instruction, and what is placed at those addresses are code blocks corresponding to each case label. So what we are doing is, instead of figuring out at runtime using a sequence of if-else statements and branches which code to execute, we are storing all the target addresses of code blocks in a jump table. And then in the code, whenever we see X of a specific value, we will just jump to that code block using the address that is stored in the jump table. So the jump table is stored in memory. It has pointers to all the code blocks. We need to do a memory access to get the address of the code block, and then we will start executing the code block. So here's an example of and there is a default case. If none of the cases match, all right, so keep putting your questions in the chat and I will answer them at once. If none of the cases match, then there is a default case. Okay, so in the code, if we look at the assembly, we compare the switch variable X to the maximum value it can take. And if it is above that range, we go to the default case. And then the address of the code we need to execute for the default case is stored right here. in the read-only data section of the address space, we have the start of the jump table L4 here, and then all the addresses of the code blocks are stored right here, corresponding to each case label. Okay, so we pre-compute the addresses, we store them in a jump table, and whenever we see switch variable value 3, we grab the address. We first grab the address of the code block that we need to execute corresponding to case value 3. Okay, there are some setup instructions that you need to execute. So this shows that corresponding to each switch value, you have a piece of code that you need to execute, and the address of the code, address of where the code is stored right here. So here is an example of, for case 1, you would translate C into assembly the usual way, and this is how you place the code for label L3 at a specific point, at a specific location in your address space, and jump to that location and start executing from that location. You can handle fall through using standard assembly tricks. Here you have case 2 and case 3. Case 2 executes all of this code because there is no break here. There's only a break after case 3. So you can jump to L6 and execute those instructions after you're done executing the instruction for case 2. So this is how you can do fall through. If you have two cases that execute the same code block, you can, if you check the jump table here, corresponding to x equals 5 and x equals 6, you have the label L7. You jump to the same address in memory because you want to execute the same code for these two labels. So you end up doing fewer comparisons. You have fewer branches. Now, there is an important lesson here. So when I ask a question from now on, I invite the online students to answer it as well. What is the trade-off? If I were to do the same with a sequence of if-else statements with a number of branch statements, what is the difference between that approach and this approach? The word I want to say here is there is a trade-off. There is a classical trade-off in computer science and how programs interact with computer systems. What is this trade-off?
For large numbers with like not much density, your tables like very large for the gap.
Right. So, but I want to talk about a more fundamental trade-off here between not having a jump table and having a sequence of if else, if else, if else. If this is true, if this is greater than this, jump here, then check again, then jump here, then check again. You know how you translate if statements, conditionals into assembly?
Like if you use a sequence of if else statements, your program has to run extra instructions.
Right.
Before you get the code block.
Poor performance.
Yeah.
You spend a lot of time executing instructions, extra instructions. Here, even if you have 500 cases, doesn't matter. You have a jump table, you grab the address, you compare your switch value, one comparison. Go to the jump table corresponding to that value, and go to the code block that the jump table encodes. Now, on one side, if we have a lot of if else, if else, if else branches, comparisons, we have extra instructions, we are spending more time. In the jump table approach, what resource are we? Nothing is free. in computer systems, in life in general. In the jump table approach, what is the resource? We are shifting the trade-off. We are saving time, but we are using something else. This jump table takes up extra space in your address range, in your memory. You have to store this jump table somewhere, right? In the other approach, if else, extra instructions, extra time. In the jump table approach, extra memory, extra space in your address space or range. This space-time trade-off will appear again and again, and you will be at the crossroads, and you will need to analyze where I can shift the trade-off and make my application run slower and save memory, and where I can consume more memory resource and save time. Here, memory is not that cheap, but it's cheap enough to store. How much memory do I need here? How big is a pointer? 64 bits. 64 bits multiplied by 8, 10, 80 bytes, even a few kilobytes today is not really a problem on server processes. So I will take the trade-off that the jump table makes of using extra memory to save execution time. If the jump table was a few gigabytes, I would think differently. Hey, memory is not that cheap. I need to, Right, so Samuel says more memory, and this is indeed good. And retrieval of a case is constant in time, very important. Even if I have 1,000 case labels, I will reach my code block that I need to execute in constant time. If your case range is not contiguous, no, you don't need 1,000 cases. So the question is, if we replace case 6 in the C code with the case 1,000, will our jump table require 1,000 entries? No, you will do something smart and divide your switch with 1,000 and then use that range. There are less comparisons because you only need to compare the switch variable to a specific value. If you see how if-else statements are implemented, you have a lot more jumps and a lot more branch statements. All right, so I want to do a revision of procedure calls. This is very similar to the ARM, the procedure call mechanism you learned for ARM processors. So what we need is a way to pass control from one function to the next. We're talking about procedures or functions. So here, when you have a function call, you go to the first instruction of the function that you're calling, and then when you return back to the next instruction in the caller's instruction code. We need a way to pass data from one function to the next. So here, the arguments are passed you copy the arguments when you call the function, the return value the callee will place the return value in a register and the caller will read the value. So this is the callee once again, and this is the caller. All right, so how memory is managed when you make function calls? We are still, you know the stack discipline. Whenever you have a function call, you create a stack frame for the function, and this is where you allocate variables that the function needs. And we do all of that with existing instructions that we have seen. We don't really have a physical stack that is built into the hardware. We allocate some space in our address range, and we call it a stack. So this is, I've already talked about that. Stack pointer, stack once again grows downward in the address space. This convention will become clear when we look at a different space or a different data structure for storing things, objects that survive beyond function calls, and we call it heap. When we put the heap and the stack together, you will learn why the stack grows downward. Stack pointer points to the top of the stack. Whenever we push something on top of the stack, stack pointer decreases by, well, this is a 64-bit architecture. Each address is 64 bits, and each object on the stack is 64 bits. So the stack pointer decreases by 8. Okay, so pushing something on top of the stack means, yes, 8. We decrement the stack pointer by 8. Popping something from the stack means we increment the stack pointer by 8. So here we have a function called mult. This is the code for mult. And when we call the function, when we look at the object code, when we look at the assembly, we're actually, call is a jump to the address mult2, the start of the function mult2. And then when we return, we go back to this point. The value is returned in RAX, and this function is moving the return value to some destination that is in RBX. All right, so this is how function calls look in assembly. So here, instruction pointer at this point contains the address of the instruction it's executing. Once again, this is like the program counter. And the stack pointer points here. After the call, the stack pointer pushes the return value on top of the stack. This is the return value. So, sorry, this is the return address. And when the return statement executes, the stack pointer takes the return address that it pushed on top of the stack and brings it, copies it into the instruction pointer and returns to the caller. Okay. This is our revision, right? You already know these things. Okay. So if you look at the slides later on, I think this will become clear. So in x86, how do you pass arguments to functions? The first 6 arguments are passed in these registers: RDI, RSI, RDX, RCX, R8, R9. This is a convention. You can break the convention. The reason we are showing this, the reason we are revising, is when you will make system calls from your user code, Linux assumes a convention, and you have to know the convention so you are able to reason about how function calls are being made, which arguments are getting updated, read, and all that. Beyond that, so if I have a caller that needs to supply more than 6 arguments, What option do I have? Memory. What is that thing in memory where the caller can place those extra arguments beyond 6? So we don't want to waste. The observation is that most callers don't really use that many arguments. So in our convention, we don't want to say like 16 registers for 16 arguments, so there's nothing left for anything else. So if there's a caller that is really very anxious to supply a lot more arguments, where should I put them? So that callee can see? No, that's I don't have extra hardware resources. All I have is registers and memory. On the stack, right? On the stack. So if you look at the stack, it's right here in front of you. Argument 7, argument 8, and you can provide as many arguments as you want, and the callee will retrieve the first 6 arguments from the registers according to the convention, and the remaining arguments, it will look for them in the callee's stack frame. This is still the callee's stack frame. The caller, we'll see in a little bit. So because the stack grows downward, the 7th argument is at the bottom. So if the stack pointer is here, what do I need to do to reach or to access the 7th argument? Stack pointer -8. Wait a second, -8 or +8? The stack grows downward. Okay, this is confusing. The stack grows downward. Remember that. You will make this mistake in the lab. Plus, to get access, if this is your stack pointer, you're the callee. Stack pointer is here. If you want to mess around with the caller's frame, you need to go up, plus. And if you want to go down in the stack to create more space for yourself, minus, 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 minus. So your stack frame will grow downward. And if you want to mess with the caller's stack frame, you go above. Plus, Semen is right. Let's see what we want to do next. Okay, so this is something. Okay, there's always something. So now if I want to hide this, this is something that is demonstrating how data flows across 2 function calls. And I think you can, we already talked about it. So languages like C, Pascal, Java support recursion, where the same function can call itself, okay? And the stack discipline is really useful when it comes to recursion. There's a lot of programming problems that are really amenable to recursion, to recursive solutions. Have you looked at recursion before in Haskell? Okay, some have, some haven't. Anything you can solve using recursion, you can solve using iteration. Now, I want to use your intuition to talk about a trade-off, but let me first do a little cartoonish recursion. All right, function yo calls who calls mi, and mi calls itself. Go from left to right. Obviously, whoever writes mi needs to provide a termination condition. Mi cannot keep calling itself till eternity. Think of mathematical problems where you have to compute the factorial. 6 factorial is 6 multiplied by 5, multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1, that's it. These kind of problems are really well suited to recursion from the programmer's perspective. What drawback comes to mind? Think about the stack discipline. Each function call will create a stack frame in the address space, and the stack frame will keep accumulating in the address space. There's a clear memory overhead to recursion, all right? But it's a programming practice that a lot of programmers really prefer. And you can solve the same problem using for I equals 0, I is less than blah, I plus plus, and do the multiplication. The trade-offs here are really intricate, and you really have to reason about, for a specific system, what is the cost of a branch, what is the cost of memory, stack frame, all of that. Once again, there is a clear trade-off between two things. Okay. There's something interesting here called the base pointer. Now, the base pointer is a reference whenever a caller calls a function, the callee, if the only thing the callee has is the stack pointer, the callee loses reference to the beginning of its stack frame. So if you provide extra arguments, what is the problem with stack pointer? It keeps changing, right? The more you use the stack frame, the more things you push, it keeps changing. So the first instruction that the callee executes, the stack pointer is somewhere. At this point, the callee can access arguments, extra arguments, other things, because there's a clear reference point. If the stack pointer keeps growing, keep shrinking, keep growing as the function executes, at some point the callee has lost sense of where is the base of the stack frame, right? So typically we use a frame pointer. It's a good practice to use a frame pointer. Whenever you enter a function, you save the first address of the first word in a register called the base pointer or the frame pointer. Now you have a fixed reference point and the base pointer does not change. Stack pointer keeps changing, the base pointer does not change. And you can use that to access extra arguments, return address, and even mess with whatever is in the caller's stack frame, because now you have a clear reference. Okay. So in x86, in the labs, when we give you disassembly, you will see these two instructions very often. Whenever a function call is made, you will see push RBP move. Okay, I'm going to let you finish this. When I enter the function, the callee, the first thing the callee is doing, it's pushing the base pointer on top of the stack. Why is it doing it? To preserve it, because the callee has the intention, it's going to do something with the base pointer. What is the next thing it will do? Exactly. At this point in time, the callee still knows where it is. One word after the caller's stack frame. So it will copy its stack pointer into the base pointer register. And now the base pointer points to the beginning of the callee's stack frame. Now, any point in time, the callee needs to access anything relative to the starting address of its stack frame, it has a clear reference, the base pointer. And it has preserved the base pointer of the previous caller. And if you look at the stack frames the chain of stack frames at any given point, you can actually use these base pointers for debugging, because you have the starting address of all the functions stack frames in the execution environment. So x86 provides a simple instruction, enter. For these two instructions, it's a pseudo instruction. No one uses it. It's a waste of, I have never seen anyone using it. You will see this all the time. So remember that if you see it in your lab 3. Okay, so to show you how base pointer and stack pointer move as function calls are made, here is a little cartoon. You call who, the base pointer, look how the base pointer is moving. Okay, the base pointer is a clear reference to the starting address of the stack frame. And we set it up by executing those two instructions. So this is how in x86 64 Linux systems, the stack frame looks like. The caller's frame, the return address, and the extra arguments are considered part of the caller's frame. And the old base pointer and everything else is in the callie's stack frame, because the callie is the first instruction the callie executes is to push RBP. So we don't consider all the extra arguments that the caller pushes on the stack as callie's stack frame. This is still the work that the caller did. Although it is to facilitate callie's execution, we still call it the part of the caller's stack frame. So when we talk about the execution environment, the word we use, environment of a program in execution, we typically talk about the chain of stack frames at up to a given point. As function calls are made and stacks frames are deallocated at any given point, what is in the execution environment? So for instance, at this point, the execution environment has 3 stack frames. At this point, 2, 1. At some point, there's 5. And this really helps us in debugging. You know, we want to check the values across the stack. So, well, then there are these, remember these boring conventions? What is caller saved? What is callie saved? You don't need to memorize any of that. If we ever want you to use these conventions, we will provide you with slide like this, and you will have it in front of you. But what it means is, if caller, the function that is calling someone, and the callie don't agree on a convention, they will mess up each other's registers. Caller will say, you know, I'm calling a function, and when I return, I'll grab something in RAX and use it for some computation. If the callie messes up RAX, then the caller has lost the value. So these conventions are agreed upon between caller and callie, which functions should be saved by the caller, and which registers are caller saved and which registers are callie saved. So for instance, RBP is the responsibility of the callie. If the callie wants to make use of frame pointer or base pointer, it's their responsibility to make sure the base pointer of the caller is preserved, because the caller wants to see its base pointer when the callie returns. So these examples are just self-study. All right, if someone wants to look at recursion, the slides are here, but we won't be doing recursion in detail here. All right, I want to start talking about pointers, arrays, two-dimensional arrays, structs. Hopefully we can finish today. Okay. So you have looked at arrays in the lab. You have a data type, int, array of a specific length, and all that. And the size of operator gives you the size, the length of a specific data type. Okay, here's a question. The first 3 arrays are not that interesting. They are arrays of primitive data types. The first one is 12 characters. The second one is 5 integers. What is the last array? Char star P3. What does it store? Okay. The semantics are as follows. This means, so someone says pointers to char, right. This means pointer, and this means 3. So 3 pointers to you, and the pointer type is character, char. It stores 3 pointers. What is the size of a pointer in 64-bit architecture? 8. So X is the starting address of the array. The second element begins at X plus 8. The third element begins at X plus 8. These 8 bytes contain a memory address, a pointer. All these arrays are placed, all the elements of each array are placed contiguously in memory. This is ensured by the compiler that, and this is very efficient in our systems, placing things contiguously next to each other where the address is changed sequentially is very efficient because processors don't just bring a single byte at a time from memory, they bring things in chunk. They try to amortize the cost of accessing memory. So contiguous allocation will be very important to our future discussions. You can do very weird pointer arithmetic in C. So here, val is an array, and val plus 1. What is the type of val plus 1? Is it a value or is it an address? It's an address. The compiler is smart enough to know that val is an array of integers. So it will automatically do the scaling for you. When you say val plus 1, it will not go to the next byte after val. It will go to the 4 bytes apart. The memory address that this statement will generate will be X plus 4 if X is the starting address of the val array. It will do val plus 1 multiplied by 4 for you, as long as you tell it that this is an array of integers. It will do the scaling for you. So val plus 1 is a valid address for the second element of the array. Okay, what is this? Is it a value or an address? Address. whenever we have an ampersand, not the best programming practice, but val2 is the value of the third element of the array, 0, 1, 2. And if we prefix it with ampersand, we get address of that element or that value. All right, so you can do, C is kind of, what is the problem here? I've underlined this statement. What is the problem? This is a valid statement in C, right? That's why for writing serious programs, very complex, high-level programs, C is frowned upon because programmers can make mistakes like this and C will not complain. You know, whatever you want, I'll do it for you. Who knows what is at val5? Another array, another variable, who knows, right? Not a safe language. The reason we still use it is it's very close to the native language, assembly, but it's not assembly. So it's somewhere in this very nice plane. It's not Java that you lose sense of how the code, translated code will look like, but it's not assembly that you have to reason about registers and all that. So Linux, a lot of system software, device drivers are still written in C. Okay, very quickly, what is this, a value or a pointer? So this and this are equivalent. You can use a dereferencing operator, or you can use square brackets. We call the square brackets syntactic sugar. There's nothing special about that. It's just the same. This looks a little bit weird, and that looks pretty. That's just, but their meaning, their semantics are the same. Okay, here's 3 arrays. Zip digit. These arrays store 5 digits of a zip code. Here's for CMU, MIT, and UCB. So we can define a new type in C using the typedef operator. At this point, I can use zip_dig as a complete type, and this is a type of array of 5 integers. Okay, so then I don't have to type square brackets all the time. I can just use the type name directly, and then this becomes a new type, and then I can use variable names to declare arrays. All these arrays are 20 bytes each, placed nicely next to each other. We can't rely upon this. We can't. Is the typedef clear? So this over here and this are equivalent because I have defined a new type, zip_dig. Okay, so I want to grab, let's very quickly, we will learn about certain trade-offs here, and those are the last trade-offs I want to talk about in this part of the lecture slides. We have already seen that here's a function that wants to return the value stored at a specific index. This is the index into the array, and this is the base address of the array. And by now, you know that this is base plus index multiplied by 4. You scale by 4 and you go to the specific element. This is how the assembly looks like. And this is a memory reference. This might still be confusing. How big is this register? All right, 32. So 8086, once again, is backward compatible. AL 8 bits, AX 16 bits, extended EX 32 bit, RAX 64 bits. We will provide you the context if we ever want you to use different registers in the same code. But most of the time, it would just be 64-bit registers. Okay, this is self-study. Okay, I want to talk about multi-dimensional arrays. So if you haven't looked at them before, let's talk about two-dimensional arrays in the context of C. At the very right is a two-dimensional array. It's like a grid or a matrix. This is a row. This is a row. And these are columns. Column 0, column whatever. So in C runtime, two-dimensional arrays are stored in physical memory using row major ordering. Each row vector comes after the previous one. The row vectors are stored contiguously in memory. So if you think of memory as a large linear array of bytes, you store the first row vector, and then you store the next row vector, and then you store the next row vector, and the different colors show the different rows or row vectors. Now, what is a different way of storing a two-dimensional array or a matrix? What else can we do? So this is row major. Row major means rows, different rows come contiguously after each other. What else could I do? Column wise. C takes the approach of row major ordering, and how we iterate over these two-dimensional arrays could really affect the overall performance of our program. Accessing memory, accessing contiguous memory is faster than accessing random memory locations. All right. So remember the example in the first lecture where I switched the ordering of the for loops, and I told you that one ordering leads to a very slow program execution. This is what I was talking about. If C runtime assumes that two-dimensional arrays are laid out like this, we need to be aware when we are iterating over different elements of the matrix, right? If we access all the row elements, we will generate contiguous memory accesses. If we access columns, we will generate a different memory access pattern. And these patterns can really hurt performance. Okay, so here is a two-dimensional array. Pittsburgh, PGH, P count 4, and you can have a two-dimensional array like this. So in memory, 15206, the first row, 15213, the second row, the third row, and the last row. Okay, let's do some address computations. So each row has C elements. If I want to grab the address of a specific row, the starting address of a specific row, I need to compute A plus, if I is the index of the row, I multiplied by C multiplied by 4. C elements in a row. Each element is 4 bytes. I is the index of the row that I'm looking for. And I need to multiply all these and add to the base address of the array. All right. So here's a code. So I want you to think and tell me, what does this return? So my definition of the, I have a two-dimensional array where each array has 5 elements. And so I have four rows. Each row has 5 columns. What does this function return? What is it returning? You get the index, and then it's returning Pittsburgh index. Is it returning the value that intersects a specific row and column? No. It's returning the starting address of a specific row. It's returning a pointer, right? It's returning the starting address of a specific row. So if you say I equals 0, it returns this address. If you say I equals 1, it returns this address. If you say I equals 2, it returns this address. So I first compute 5 multiplied by index because I have 5 elements in my array. And then I scale it by 4 because each element is 4 bytes. And I reach the starting address of a specific row. Okay. So the base address of the two-dimensional array multiplied by the number of elements in the array multiplied by the size of each element. And I can use leak instructions to generate the address. What if I want to generate the value, the address of a value at a specific row and column? Sorry, PGH IJ. So I will need to do all of that. Plus, I will have a second index, the column index. And I will need to add the column index scaled by 4 to reach the specific point inside the specific row. Okay. So how will my code look like? Same as before, 5 elements in the array. This time, I'm going to add the column index and then scale the whole thing by 4 and add the base address of the array. And this will give me the address. This will give me the address of the specific element at the intersection of a row and a column. If the function provides me with the index, which is a specific row, and dig the specific digit inside that row. So this address is the base address plus 20 multiplied by index, because each of this row is 20 bytes. And index means if index equals 0, we're talking about this address. If index equals 1, we're talking about this. If index equals 2, we're talking about this. Once we reach here, we need to add digit. It's either this digit or this digit or this digit or this digit. We need to multiply it by 4, and digit comes in register RSI, whoever calls this function. So these address computations could be really expensive. We write really useful applications, use very interesting data structures. And if you ever look at the disassembly, There will be a few memory reference instructions, but there'll be a lot of these address generation or address generating instructions. And this is all computation. This is all compute. I want to contrast. Okay, one note. At first sight, this looks complicated. This is not at all complicated. This is basic, like base address plus 4 multiplied by 5 elements plus once I'm inside the row, this multiplied by that. But we are going to learn something soon. All right, what's a multi-level array? A multi-level array looks similar to a nested array with the following difference. This array is an array of 3 what? Pointers. 3 pointers to an integer. And those pointers are stored here as MIT, CMU, UCB. And those arrays are defined here. So this is once again, I'm using a level of indirection to create a 2-dimensional array or a multi-level array. Okay. So in memory, in my address space, I have 3 pointers stored, 3 addresses stored contiguously. And each of these pointers point to an integer array. Does this look like a 2-dimensional array? Kind of. It has some interesting properties, but you can say univ ij to grab a specific value in CMU, UCB, or MIT array. But there is a subtle difference. If I want to return a specific value here or here, what does my code look like? So here's a function. This is the index of the digit. And this is the index of something here. Okay, I want to say quickly, size t is a data type that C provides, and you need to include a special header file. We will do that in the labs. Here, this is the largest integer possible on a specific machine. So if you're running on 64 bits and you want to guarantee that I want to use the largest possible integer type, you can use size t. This is C's attempt at platform independence. Okay, it doesn't always work. It's not as robust as Java, but most of the time it works. At least it's an attempt. Okay. Okay. So why are we doing this? Shift arithmetic left by 4. We are multiplying RSI. RSI is here. The second argument is in RSI. We are multiplying the digit by 4 because each digit is 4 bytes. Okay, let's start with that. So someone is asking, I equals 0 will be here. I equals 1 will translate to multiplied by 4, and so on. But that is not enough for me to access the value. What am I doing here? I'm taking the base address of the university array and adding what is in RDI? The index into the university array, right? And why am I multiplying by 8? Why is the scaling factor 8? The size of a pointer. University is the base address of the 3-pointer array. And then to go somewhere inside that array, I am scaling the index by 8. And the add instruction adds that to RSI, which is the position or location of the integer in the CMU, MIT, or UCB array. What is interesting about this add instruction? Right. Anyone else? What is interesting about the add instruction? Anyone online? It's an arithmetic ALU instruction, but it's also doing something else. Look at the addressing mode, uni parentheses. What does it tell you? It's doing a memory reference, right? Why is it doing a memory reference? What is this bringing from memory? Where RDI is this index. Right. It's bringing the pointer to one of the 3 arrays, CMU, MIT, or UCB, right? We first need to grab the pointer to one of those arrays, and we then need to index into those arrays. And then we bring the value in one of the arrays into EAX. Okay, at this point, comparing to the nested arrays, the address computation in the nested array implementation, what is the difference between multi-level and... So there, I was trying to grab the value, I was trying to compute the address of a value at the intersection of a row and a column. This is kind of similar. I go into one of the 3 arrays and bring a value. But what is the difference between? This is a property of the arrays. I'm talking about the address computation. To reach the value, I did some address computation in the nested array implementation, and I did some computation here. What is the key difference? Well, I could have done it differently. I could have done reorder instructions. All right, so this is the nested array. Anyone online? And this was my address computation. This was my address computation. And then there was a memory reference, right? So the address computation was a little bit tricky, you know, PGI, Pittsburgh plus 20 multiplied by index plus 4 multiplied by digit. And this is my multi-level array. This is my address computation, and this is my reference to get the value. Do you now see the difference between the address computation for the nested array and the multi-level array? What is the key difference?
Reading memory twice.
You're reading memory twice just to compute. On this side, what happened here? All right, on this side, just to compute this address, you are first doing a memory reference to read the pointer stored somewhere in memory, and then doing the scaling to reach a specific element into one of the arrays. and then you're doing an extra memory reference to read the actual value. Here, you compute the address and you go to the value, because row vectors are placed contiguously in memory. If you know the base, you can go anywhere. Here, the semantics of the multi-level array are that you need to store the pointers in a separate array, and they should point to the actual values. So you need to grab the pointer first, then do your remaining address computation, and then do the memory reference again to get the value. Okay. The power of multi-level arrays is that each of these arrays could be variable width, variable in size, but you pay a price. Memory references have a cost. We try to minimize memory references as much as possible. A typical processor is running at 1 gigahertz. The clock switches 1 billion times a second. And each cycle, the processor is trying to do something. Whenever you encounter a memory reference, for 100 cycles, the processor cannot do anything. It has to wait for memory. Memory is slow. So we try to minimize memory references as much as possible. So the way you write your programs, sometimes you need to reason about how many memory references will this specific pattern of programming will generate. Okay, we talked about structs a little bit in the last lecture. Structs in C allow you to pack together, to combine different data types into a single heterogeneous data type. In this case, I have an integer array with 4 elements with an integer I and a struct, a pointer to the next record. Okay, and I can combine them together into a single type called record. Okay, where might you use a structure like this? A linked list, where each record has a pointer to the next record. Okay, this is how you create linked lists in C. So now I have an object called record. This is poor man's object-oriented, And the fields of the struct are laid out in memory contiguously. So first 16 bytes for the array, the next 8 bytes for size t, and the next 8 bytes for the pointer next. And if I want to grab a member of a struct, I use the struct this operator. So RAIDX will give me the first element of the array A stored inside record. We will introduce structs in detail in the next week's lab. This is just a very quick overview. So this operator, whenever I have a pointer to a record, to access a member of the struct, I can use this operator. Struct reference or struct member reference operator. And this is giving me the address of that specific members element. And once again, I can use leak to compute the address. These offsets here, 0, 16, 24, 32, they can be very easily encoded with the displacement in the address mode instructions. So RDI is the base address of the struct, plus RSI is the index into the array multiplied by 4 to access a specific element in the array. And once again, this is not safe. The programmer can say 5 or 6, and you will get something here, but C will not stop you. It will look like an array access. Okay, this is some code to follow the linked list. Okay, I want to talk about last thing, alignment. So alignment is really important aspect of modern computer systems. So what do I mean by alignment? So here I have a structure S1, and this is unaligned. The starting address of the structure is P. A character is 1 byte, P plus 1, P plus 5, P plus 9, P plus 17. The problem is, we see the problem in a bit, but when you have addresses of primitive types like integer that are not a multiple of 4 or 8, depending on what type it is. So integer k equals 4, long k equals 8, and double k equals 8. If the address is not a multiple of k, there is an inefficiency that I'll explain in a minute. So what compilers do, they do some padding to align all the addresses of all the native. Native means all the data types that come in the language. So record is not a native type. It's a special type that I have created using a struct, and it's an object that is only known to me, not to the public. Integer, double, long, these are all native types. They are part of the language spec. Okay, a native type must be aligned to k bytes, where k is the size of the type. So here, if the starting address of the struct is P, then this integer is placed at P plus 4. This integer is placed at P plus 8, which is a multiple of 4. And then to place the double at an address that is multiple of 8, the compiler does a padding of 4 bytes. So the address P plus 16 is a multiple of 8. The reason we need to do that is, if you focus on this diagram here, the processors don't read 1 byte from a random location in memory. Memory is logically organized into words of 64 bits, and you read 1 word at a time. Word number 0, word number 1, word number, so these are byte addresses. Byte number, word starting at byte 8 to byte 15, no. So if I place my 64-bit word, these are byte addresses. Word addresses would be 0, 1, 2, 3, 4, 5. If I place a 64-bit word at byte address 3, what is the problem? Processors do 1 memory access for each word. They logically divide memory into 64-bit words and read a word at a time. So if I say byte address 0, the processor will bring 64 bits. If I say byte address 8, it will bring 64 bits. If I place a 64-bit word, a quad word, at byte address 3, what is the inefficiency? We need 2 memory reference instructions. We need, not instructions, we need 2 memory references to read the bytes that make up a single 64-bit word. Right? If my 64-bit word is spread across these 2 logical words, then I need to do 2 memory references and then somehow shuffle the bytes together to make up a 64-bit word in my registers. If I place the 64-bit word at 0 or 8 or 16 or 24, the processor does one memory access and brings the whole word. Doesn't have to do any shuffling, nothing. This is what we mean by alignment. And you can place a character. So based on this, what is the restriction? What kind of addresses can characters take? Can I place characters anywhere in memory? Or do I have certain restrictions on what kind of addresses characters, char variables can take? Character is 1 byte. So I can place it anywhere, right? And the processor will do one access to read one character, no matter where I place it. Similarly, think about 4-byte integers. If 4-byte integers are part of one of these words, then I need one access. If they're spread across 2 logical words, then I need 2 accesses. This is not on Intel x86. This is not a correctness issue. The processor, the system will still work correctly if I don't take care of alignment. This is a performance concern. So you have to distinguish between correctness and performance. So here we're talking about doing things more efficiently by aligning all the data types in memory where we have this logical view of memory. So no restrictions on the address of character. For a short, it needs to be a multiple of 2. So the lowest 1 bit needs to be 0. For int and float, it needs to be a multiple of 4 bytes. The low order 2 bits should be 0. And for 8 bytes, double long pointer, they should be aligned. So the address is a multiple of 8 bytes. So this is an example once again. So there is a restriction on the overall structure placement. And the restriction is each structure has an alignment requirement K, where K equals the maximum alignment requirement of the data types that make up a struct. So in this struct S1, double has the largest alignment requirement of 8 bytes. So this struct S1 should be placed in memory at a starting address that is multiple of 8, and its length should be a multiple of 8. Why is that? Because when we have arrays of structs, we need to satisfy the alignment requirements of each member of the struct. And the only way we can do that is by ensuring that the largest alignment requirement of all the members, across all the members in the struct, are met.
So any example like you got there, what if you have the delta for the like your doesn't that still satisfy one not satisfy the overall one?
You can satisfy the alignment requirement of an individual struct by moving things around, but when you put them in an array, there you will have a problem. So if I have another struct after this and another struct after this, if I have an array of structs, I still need to make sure that all the alignment requirements are met. And the only way to do that is to take the maximum alignment requirement across all members in the struct and make sure that the length of the structure is a multiple of that K max, and the starting address is a multiple of K max. Now do a homework, try to move this to P+1 and only do a padding of 2 bytes and satisfy the requirements of all the individual members inside the struct, but then try to append another struct and you will see a roadblock. The only way to satisfy requirements, alignment requirements, when you put structs together is to those 2 conditions. All right, so you have to meet the overall alignment requirements. Sometimes you have to do padding at the end of a struct, and this is called external fragmentation. And the padding you do inside the struct is called internal fragmentation. So the compiler will take care of all this padding, both internally and externally, making sure that everything is properly aligned in memory, so the memory systems behave optimally and not inefficiently, where you have to do multiple references just to bring a single word if you do some weird placement of native data types and structs. So here is an array of structs. If we open up one element of the struct, we see that the alignment requirements of each element are met, and the alignment requirements of each member of each element of the struct array are also met if we do the proper padding and if we follow the guideline in the previous slide.
Do you compile way to the order of the like elements of the struct, or do they shuffle them?
Compilers cannot reorder the members because then the semantics of the programmer's intention is not satisfied and the program will not work. But there's something else. The programmer can do something smart. All right. So final. Next week, I don't want to do x86. It's
Like one of the coverage that they like calculated that like compile time anyway. Like what would be something that the compiler for like implicitly like or like secretly just reordering the structure?
because if in the program, all right, so the compiler could do that. But then the compiler will have to analyze all the rest of the code and make sure that all the members are reshuffling and all that. Okay, so let's see one last thing. Okay, that one last thing is missing. You can actually, how you place the members inside the struct. So the padding you do is a waste of memory. It's not really useful. It's only there for alignment purposes. If you have a char short int, sorry. If you have members char int char, how much padding you need to do to satisfy the int requirement if this begins at 0? So here, how much padding I need? 3 bytes. And do I need padding here? No. And do I need padding here? So 3 plus 1, 4, plus 4, 8, plus 1, 9. I need how many bytes? 3. Now imagine if I declare my like this, and this starts at 0. Do I need padding here? Do I need padding here? Do I need padding here? All right. So we have seen that the way you order members inside a struct, you can mitigate some of the overhead, memory overhead due to padding. And the general rule is the largest data types should begin first, and then the smaller data types should come after. And this is not a rigorous mathematical thing. This is an empirical observation. And I just made it up and it worked. In the slide deck, there'll be a couple of more slides to explain this more clearly. For some reason, these slides are missing from my deck. I don't know. Okay, but you get the idea. You can save space by reordering the members inside the script and mitigate the padding overhead. Take care. We'll see each other next week. I'll be uploading a problem set, the first problem set for your practice, and take care.
I think how much slide you upload on the website.
What?
Most pages are missing. So like on the website of the lecture 2 slides, we cannot see anything about starting from the nested array. So it ends. Let me see. Oh, you uploaded new slide today?
No.
Actually,
Yeah.
Oh,
Go back to the website.
oh yeah. Oh,
It says slide 52 onward, Thursday lecture.
oh,
I will always do that.
oh, right. So it's. But when I downloaded it yesterday, I didn't see it.
No. I did it today.
Oh, right.
All right. Take care.
Which section or chapters we read?
I'll do it on the website. I'll do it.
Thank you for the very quick question. Do we have any access to the lecture slide?
Yes, they're on the website. No, but I put them in the morning.
Okay. So when I see the
Yesterday?
no, when I rewatch the lecture, I see the link at the bottom of the lecture, but not prior to the lecture.
No, but they're online. These slides are online at this point. I will do this always.
Okay, great. Thank you.
I started doing it this week.
Thank you.
All right. Thank you.
One question about the case statement
Yeah.
that someone else told me. If I understand your response, like if you had instead of case 6, have case 1,000. Why don't you need to have 1,000 entries?
Because if you have actual 1,000 cases, you will need a jump table of 1,000 addresses. But if your labels are too big, you can normalize the labels first and then do the access into the jump table. You can normalize. So if the programmer writes code like case 10,000, case 20,000, case 30,000, you can divide that switch by 10,000 and then use the index to get into the jump table. You don't need 10,000 addresses because the programmer is saying that my switch variable can take these values. You can normalize your switch variable when you write assembly. You can divide it by 10,000 and then use the index into the jump table.
So in that case, what if the programmer passes in 500 somewhere in the code?
You will have to, yes, this is, you have to tackle such cases. So if the programmer passes 500, you divide it by 10,000, what is it, 0? And you will have a special case for 0, default, or something.
Okay. So it would handle it based on what. Okay. Cool. Other thing about that is that can you have case labels that are not integers?
No,
But like in Haskell, you have like a match. You can do that with like.
not in C. Not in C. Not in C.
not in-
You cannot have floating point cases. Because that range will then become a yes. And then how will you write assembly code?
Right, yeah.
Someone asked a good question. Why are the comparisons, number of comparisons less in case? I think I will have, I put it on the forum, the answer with an example. I'll try to do that. Why the number of comparisons in switch are less than if I have an if else implementation.
there even any comparisons in Switch?
You have to do it, right?
Is there like, like